So in this video we're going to complete these problems and these problems. And we're going to start with the look at what division does under this radical. Now here's the square root of 100 over 4. And I know that a fourth of 100 is really just 25. So if I wanted to simplify what I saw, I could say 100 over 4 turns into 25, and I know that the square root of 25 is 5. But that's when I just simplify something, according to order of operations. But I wonder if we could break this apart, because, really it's just the top of the fraction over the bottom of the fraction. So is it okay to break it apart and to experiment with it and see if it's the exact same as 5? So what's the square root of 100? 10. What's the square root of 4? 2. And I'm just bringing the right side down, but is 10 over 2 the same as 5? Totally. So if you really believed in the last thing and thought it was clear, then there's no reason why division wouldn't work as well. So what this shows is that if I have the square root of a over b, I can just break that apart into the square root of a over the square root of b. And we'll make that example I just gave you as the go-to example. So if I had the square root of, actually I'll just say 10 over 3, then that's the same as the square root of 10 over the square root of 3. I wrote that in red, but write that down. Sorry about that. Now we have slightly different limitations on this. Now where a is greater than or equal to 0, and actually I think that would be fine if it was 0, and where b is greater than or equal to 0, because you can't divide by 0. And then also these are all dealing with non-negative answers. So that is the quotient property of square roots. Now rationalizing the denominator. The instructions for these say simplify. And through most of your time in math, you've seen something like 10 halves. And if you were told to simplify that, I think we can all agree that saying 10 over 2 is more complicated than 5. So it always made sense to me that if you simplified something, you'd get something that looked maybe a little bit more elegant. And similarly, the square root of 49, I don't know what that is as a value, but if I simplify it and I tell you that it's 7, that's more clear to me. But these rationalizing the denominators problem, really, sometimes they look actually more complicated by the end of the problem. So basically what this is saying, to truly simplify problems like this with radicals, you cannot have a radical in the denominator. What that means is that the square root of 5 over 3, that's okay. But the square root of 5 over the square root of 3, that is not okay, and you'd have to change this to get rid of that fraction having a radical in the denominator. So we're going to use that quotient property, and we're going to rewrite the square root of 10 over 3 as the square root of 10 over the square root of 3. So I've just rewritten the top and bottom separately. But when you've done problems in the past, there's been times where maybe you took a value like x and you multiplied it by 1. But you didn't write it as times 1. You really multiplied it by 5 over 5. Maybe you had to combine fractions or do things to make this happen. But if I multiply something by 5 over 5, I am not changing its value. I'm just multiplying it by 1. So even if I multiplied something by q over q, that would not change it. So what I'm saying here is that we are going to take the denominator and times it by itself. But if I did that only to the denominator, I'd change its value. So you also have to multiply the top by the square root of 3. And really, what this thing that I've written right here is, it's just the number 1, because it's the same deal. So as I multiply these across, you're going to see in a moment why you would do this. Well, the square root of 10 times the square root of 3, I can combine that into one radical. and the square root of 3 in the denominator being multiplied by itself, well, no matter any time you do that, you end up getting rid of the radicals. You're going to be left with 3. And so, assuming that this is not break-apartable, that's a terrible way of describing it, I'm sorry about that. Assuming that no perfect squares go into it, we're done. Well, 25 is not going to work. 16 is not going to work. And so I tried 5 squared, 4 squared, 3 squared, 9 is not going to work. And then 4, there's the part of me that wants 4 to work, but that would end up not being the case. 4 times 7 is 28. 4 times 8 is 32. So even 30 being such a big number like it is, in that radical, that's totally simplified. So we're going to stop there. And if I look at what these say, well, yeah, we did simplify this because we no longer have a radical in the denominator. And then you'd obviously simplify if you could cancel out any fractions or anything like that. But no, this does not become the square root of 10 because this radical has 30 under it. And this is not in a radical. So you cannot say that it's the same thing over there. So make sure that you're checking these in Wolfram Alpha and plugging in real numbers whenever possible to see that things make sense. Okay, I'm going to clear the ink on this page and move on to number 2. I'll have more room this time, so it should work out nicer. This time they have it broken apart to begin with. So I have the square root of 2n over the square root of 6. And if we felt like it, we could go about this 2 different ways. I'll go about it the way I think most students would. Well, you just learned about this tool, so maybe you're like, well, I can't have that 6 down there, so I'm going to multiply by the square root of 6 over the square root of 6, which is just 1. So that then now in my numerator, I can put these two deals together, which is 2n and 6, and since it's all going to be multiplied out, the numerator is just going to be the square root of 2 times 6, which is 12. And then n stays under the radical. And then down here I'm going to have 6. But unlike the last one, we're not done. Because if I have the square root of 12, I know that I can pull a perfect square of 4 out. And when I pull 4 out, it becomes 2. Square root of 3n over 6, and then this simplifies to give us the square root of 3n over 3. And we'll box that. Quick little side approach. Now look at this. I had square root of 2n over the square root of 6. I'm like, well, hey, I got the quotient property, don't I? So couldn't I just think of this as the square root of 2n over 6? And if I did it that way, couldn't I just say that's the square root of n over 3? And then if I wanted, break it apart and then rationalize the denominator, that's the word for what we're doing, and then I'd have 3n over 3. And if you do the same problem 2 different ways and you get the same result, that should probably build confidence in how you did this. So I look at this and I think it's pretty darn good. 2 different ways of doing the same problem, and one might be better than the other, or one might be worse. 3. Make this an on-your-own problem. I'll put the answer up in just a moment. 3, 2, 1. Square root of 14 over square root of 5 was rewritten, multiplied by 1, which was square root of 5 over square root of 5 to rationalize the denominator. 5 and 14 gave me 70. And then square root of 5 times square root of 5 is 5, and it no longer has a radical in the denominator, so it's good to go. And, I see 70, and I'm like, that's such a huge number. Surely something can come out of it. 49 doesn't fit in. 25 doesn't. 16 doesn't. Well, 9 times 9 is 81. 9 times 8 is 72. That's not working. Does 4 work? Well, half of 70 is 35, but then when I try to take another half of that, I'll get a decimal. So not even 4 works, and then 1 doesn't take you anywhere. So even though that's a really large number, you'd be done there, but it's good to kind of think about it and check yourself out. 4 has a variable Let's make this another OYO problem. So right after I rewrite this, you'll see the answer. So pause this. Early on, I noticed that 6 over 12 would cancel out to give me 2 in the denominator, and then I rewrote it broken apart. And then once I had it broken apart, I wanted to rationalize the denominator, and then I had square root of 2y over 2. Now this might seem like a lot of kind of silly work to really make something that didn't look all that confusing, maybe the same amount of confusing. And I would agree with you there. I don't think that you'd be wrong if you felt that way. But what you're being able to do here is you're developing a tool that you'll be able to use later on for higher level applications. And I actually think these problems are kind of fun. I don't know why I have this slide on here a second time. Hopefully that means that there's not anything more to do in this video. So we'll stop this video here and just hope I didn't screw something up.